In 2009, a satellite circled Earth, methodically scanning and sorting the wavelengths reflecting off the planet's surface. Researchers were looking for the spectral signature of carbon dioxide when they noticed something baffling, an unexpected wavelength of unknown origin. They tried looking at Earth with only this wavelength, and saw the planet covered in a red hue of varying intensity. This couldn't have been reflected sunlight because it was a wavelength that never escaped the sun's outer atmosphere, and it didn't correspond with densely populated areas, suggesting it wasn't human-made either. In fact, it was emanating from places with lots of plants. The Amazon basin, northern evergreen forests, and croplands of the Midwestern US were all ablaze. So, what was going on? Plants and other organisms use light to grow by way of photosynthesis, but that's just one of 3 ways that light entering a photosynthetic organism is used, and this is the key to solving the mystery. To understand the others, we need to begin with photosynthesis. During this process, sunlight hits structures within a plant's cells called chloroplasts, which are packed with chlorophyll pigments. When chlorophyll molecules absorb light, some of their electrons become excited. They go through a series of reactions which transform light energy into chemical energy. This powers the conversion of carbon dioxide and water into glucose, the simple sugar plants need to grow. And of course, this reaction generates an important byproduct. Photosynthesis, which is constantly being carried out by plants, algae, and bacteria, produces all of Earth's oxygen. But plants regularly absorb more light than they're able to consume. For instance, over winter, the frozen leaves of evergreen trees can't photosynthesize at their usual rate, but they're still exposed to a lot of sunlight. If not dealt with, the excess light can damage their photosynthetic machinery. So, the second way plants use light is by transforming it into heat and dissipating it out of their leaves. The third way plants interact with incoming light is by radiating it back out at a different wavelength, producing what's called chlorophyll fluorescence. During photosynthesis, the chlorophyll's excited electrons move through that series of chemical reactions. But as some of the excited electrons fall back to their ground states, they emit energy as light. Overall, about 1% of the light absorbed is re-emitted as wavelengths at the red end of the spectrum. It's such a small amount that you can't see it with the naked eye. But plants the world over are fluorescing as they photosynthesize. And this is what's caused the Earth's baffling red glow, as observed by satellite. It was an accidental discovery, but a huge breakthrough. Tracking chlorophyll fluorescence from space allows us to watch the planet breathe in real time and monitor the health of ecosystems worldwide. Previously, researchers used levels of greenness as the main estimate for plant health, because plants generally change colours or lose foliage when they're stressed. Higher levels of green typically indicate healthier plants. But this measure can be unreliable. In contrast, chlorophyll fluorescence is a direct measure of photosynthetic activity. It can help us infer how much oxygen is being released and how much carbon is being absorbed in a given system. Drops in chlorophyll fluorescence may also occur before visible signs of plant stress, making it a timely measure. Scientists have already used chlorophyll fluorescence to monitor harmful phytoplankton blooms and track the effects of drought in the Amazon and Great Plains. Going forward, we'll be investigating photosynthesis from space and gauging how best to support our silent friends who already do so much for us. Besides helping us keep track of our ecosystems, we rely on satellites to keep our daily lives up and running. So what would happen if they all just disappeared? Find out how the world would react and the odds of this actually happening with this video.